Okay, so in today's lecture, we will go through the material for the whole week. So the recorded lectures for the 3 recorded lectures were posted for you to watch. I'm assuming that you did. Okay. So today we're going to go through the material. We're going to solve questions, and we are going to answer your questions about the week 8 material. So in this week, in those lectures, we covered the electric potential energy, electric potential, and the DC circuits, currents, potential difference, resistors, parallel, series, combinations, and solving for power as well in those circuits. So if you have any questions, please ask, or I will go through this material briefly, and then we can start solving questions. Any questions so far about those 3 lectures that you guys attended? No questions? Yes, go ahead. Today and Friday will be for the whole week, so feel free to ask any, a question from the last lecture as well, whatever you want. Do you have any questions so far? Okay, later we'll do that later. So when it comes to electrical potential energy, it's not going to be that much different from what you have seen in gravitational potential energy. We are interested in the energy change. We are not interested in the absolute values of those electric potential energy. However, we're interested in the change in the energy. And in the first lecture, we have explained and demonstrated how to set up your problem to properly calculate the electric potential energy between 2 levels. And we have seen that we have 4 combinations, 2 for the negatively charged plate and 2 for the positively charged plates, where you have electron or proton, negatively charged particle, or positively charged particle for both cases. That's why we have 4 combinations. Which basically, if you have a negatively charged plate, we said that we will be using that plate as our reference for the displacement. So this is going to be the y equals to 0. And then the positive direction would be pointing toward the side of the particle, the charged particle. So in this case, you can see that this is very important, and defining or adopting a systematic approach to make it easy for you to calculate the potential energy. However, keep in mind that any charge you release in the existence of an electric field will move such that its electric potential energy decreases. So if you release this electron, for example, on top a positively charged plate, then this electron is going to move away from the plate toward decreasing its electric potential energy, which means that the electric potential energy at this point is greater than the electric potential energy at that point, B. So always keep this in mind. And you'll see this when you calculate the difference, the delta in the electric potential energy. In uniform electric field, we have uniform forces. Because the electric field is uniform, this means the exerted force on any particle in that electric field will be also uniform, because electric field is uniform. So this is going to result into a constant acceleration, which means that you can still use the kinematics equations for charged particles in uniform electric fields. No difference. Also, the energy is conserved. Conservation of energy applies as well, which means the electric potential energy plus the kinetic energy before equals the electric potential energy plus the kinetic energy after. If you move U1 to the right side and EK2 to the left side, you're going to end up with delta U equals to minus delta EK. Okay, so again, finding the acceleration will later on allow you to use the kinematics equations to calculate either displacements or the velocity. It depends on what you are looking for. Then the electric potential, which is also related to the electric potential energy. The electric potential is an electric field dependent, does not depend on the charge. However, the electric potential energy depends on the charge. It is related to the charge that does exist in a position in the field. So the electric potential is indeed joules per coulomb, and the unit for the electric potential is volt. Now, if we have, or if we are interested in the electric potential energy difference or a change, then we also be interested in the electric potential difference as well. So the relationship is given by delta U equals to Q delta V. So it depends on the potential difference, and it depends on what type of charge the motion will be. In all cases, the charge is going to move in the direction that makes its electric potential energy decreases. If it was released in a field. Unless there is an external force that opposes that field, is moving it in the other direction. This is similar to what we have seen in the gravitation potential energy, when we said that if you lift this calculator up, you're doing a work opposite to the electric, to the gravitational force, which basically you are increasing here the gravitation potential energy. Same thing happens to the charged particles in the fields. Then we talked about the electric current, and we introduced Ohm's law, and we said that the current is the time rate of the charges of flow, which means the amount of charges that flows per unit time. So if delta U equals to Q delta V, and delta U equals to minus delta EKV, then I have this expression that relates the potential difference to the electric potential energy difference to the kinetic energy difference. Delta U equals to Q delta V equals to minus delta EKV, delta EK. The current, the time rate of the charges flow, which is the amount of charges that flows per time unit. And here we have coulombs per second, the amount of charges that flows per second. The unit for the current is amperes. Then Ohm's law basically relates the potential difference to the current by the definition of the resistance, where the resistance is the ratio of the potential difference to the current. This resistor works like the tap. It depends on the value of the resistor. You can control the amount of the charges that flows. The higher the resistance, the lower the charges that flows. So the relationship between the resistor and the current, the resistance and the current is inverse proportional. The higher the resistance, the lower the current. For the same potential difference. If you fix the resistance and increase the potential difference, then the current will increase as well. It becomes proportional to the potential difference. Ohm is 1 volt per ampere, which is the unit of the resistance. Then in DC circuits, we introduced the components that we will be seeing in the circuits. And we said in our circuit, we have a component that is responsible for generating energy or supplying power, which is the battery in this case. And then we have components that consume power, which are resistors, or light bulbs are also from the same type. And we assume that our conducting wires are ideal, which means they have zero resistance. Practically, they're not zero. However, they have very little resistance that we can ignore in our course for simplicity and treat them as zero resistance wire components. Then we have the switch that if you open, there will be no current flowing through because it will act as an infinite resistance. Infinite resistance, delta V divided by infinity, it's going to give you 0. So if you have an open switch, no current is going to go through that switch. However, if you close the switch using the assumption or the convention that we have agreed upon that we're using ideal components, then this switch will have 0 resistance. So this closed switch is going to act like a wire, an ideal wire, and it's closed. So if we have an open switch, our circuit is broken and there is no current going into the circuit. If you close the switch, then the current is going to flow in the circuit. So here in this case, 2 light bulbs, each has a resistance of 12 ohms. If you want to calculate the current, what would you do? You find the total resistance, right? And then you divide the potential difference that you have here, which is 6 volt by this total resistance. This is Ohm's law. You get the current. We talked about the topologies of the circuits. Series resistors, parallel resistors. You should be able to distinguish between which resistors are connected to which in series or in parallel. Those are one of the common mistakes that students do when they are analyzing circuits. Identifying the correct descriptive to their orientation in the circuit. Are they connected in parallel or are they connected in series? Sometimes they have to do one simplifications in order to get the result that they want. We'll talk about that later on when we come to it. But let's reintroduce the definition of the series. When do we call resistors connected in series? Two resistors connected in series when they have one terminal being shared and the same current going through them. So in this case, if I look at those circuits, at this circuit, I can see that those resistors R1, R2, and R3 are all connected in series because R1 and R2, they're sharing this terminal, and then the same current is going through R1 and R2. Same thing applies to R3. R3 and R2 are in series. The same current goes through R1, R2, and R3. So all of them are in series. What about the parallel? I call two components connected in parallel when they're both terminals are where they're sharing both terminals. So if you look at R1 and R2, every component here has two terminals. And I can see that R1 and R2, they're sharing both terminals. And also R3 is sharing that with them. And this makes three of them connected in parallel. And if you have two components connected in parallel, this means they share the same potential difference. This is extremely important. So the delta V I'm seeing here, this delta V is the same across R1, the same across R2, and it's the same across R3. So the general expression for calculating the equivalent resistance for three resistors that are in parallel is the inverse of the equivalent equals the summation of the inverses of all of them. So this is the general expression, which is 1 over R equivalent equals to 1 over R1 plus 1 over R2 plus 1 over R3. This is the general expression for calculating the equivalent resistance. Now, if you connect an ideal conductor, an ideal wire across a component, you've shortened out this component. Why? Because charges are going to, or the current is going to see two paths here. One path has a resistance, which is going to cost them, it's going to cost that current, right? Power consumption there, power will be consumed. And a zero resistance path. And in this case, the current is going to take the zero resistance. Now, this is ideal. Practically, there is a limitation that may result into an excessive increase in the current that may cause other consequences. But that's what's going to happen in short circuit. If you have a wire, this wire is connecting both terminals of the component this way. By mistake, for example, you bypassed this way, you have bypassed this light bulb, which means that you have shortened out this light bulb. All the current I, in this case, is going to go this way. And the current going in here would be zero. Now, the relationship for the equivalent resistance for two resistors in parallel is given by this expression. R equivalent is the product divided by the summation. So if I have R1 and R2, R1 and R2 in parallel this way, then the R equivalent is the product times the summation. So in this case, this is going to be R1, R2 divided by R1 plus R2. This is This case is for the two resistors that are connected in parallel. You can use this expression right away. If you have more than 3 resistors, then you have to use the general expression. Now, if you assume that in this case, this wire is R1 that has a 0 resistance, and this light bulb is the R2 that has a finite resistance, R2. In this case, if you apply this expression to find the equivalent resistance for this light bulb that has this wire in parallel, if you substitute R1 with 0, R equivalent right away is 0, which means that you have shortened out this light bulb. Light bulb's resistance does not contribute whatsoever in this equivalent resistance, which means it is as if completely out of the game. And then we've solved several DC circuits. We've seen several examples. For example, some of the common mistakes that is done is identifying the series parallel in circuits. For example, if I ask you, is R1 and R2 connected in series or parallel, what would you say? Here in this circuit. Is R1 and R2 in series or parallel? R1 and R2 are in series. You agree? You agree? You do? You agree? Well, let me tell you that R1 and R2, they're neither in series nor in parallel. If you go back to the definition of the parallel and series, you will see that although they are sharing one terminal here, but the current going through them is not the same. This current is going to split into two currents, which means they are not in series. Are they in parallel? No, they are not in parallel because they only share one terminal. They don't share both terminals. If they share both terminals, then they have the potential difference the same across. So R1 and R2, they're neither in series nor in parallel. Whatever you try to look. But what about R2 and R3? I'm talking about the same circuit. So let's talk about this circuit. What about R2 and R3? Are they in series or in parallel? They are in parallel. That's correct. But what about the equivalent now of this R2 and R3? This R2 and R3 has an equivalent resistance, right? What about this equivalent resistance of R2 and R3? Is it going to be in series or in parallel with R4? In series. Why? Because if I am to draw this, I would be having a resistor here, and then this is R equivalent, and then this is R4. Indeed, R1, R equivalent, and R4, three of them are in series. Look at the current. So now we know what does series and parallel mean and how to identify components that are in series and parallel. So we solved several examples, and then we introduced the power, and we said that the power equals to the potential difference times the current for any component. And we also said that the power, the expression for the power can be modified, or we can derive two more expressions for the power. If we say that this power is delta V times I, so this is finding the power in terms of the potential difference and the current. Fine. If I substitute this delta V with R I, so what do I get? I get a second expression, which is finding the current in terms of the resistance and the current only. So in this case, power would be R I squared. Sometimes you have the resistance, and you have the current that goes through this resistance. Then would be easier, makes sense to use this expression, Ri squared. Sometimes you have the potential difference across the resistor and the resistance. In this case, you substitute I with delta V over R. And the third one would be, so this is the second, this is the first. Substitute I with delta V over R, you get the third one, which is delta V squared divided by R. Why? Because I is delta V over R. In this case, you have delta V over. So it depends on what you have. Those are some expressions that are easier to use, already modified, such that it depends on what you have. So this is the third one, delta V squared divided by R. So any questions so far? We went through the whole week 8 material briefly. Of course, relying that you have watched the lectures, right? Relying that you have already watched those lectures and you know what I'm talking about. If not, that's different scenario. So, any questions so far? Questions about what we have talked about? Yes. One, two, and four? No, they're not in series. One equivalent of 2 and 3 and 4. Those are in series. But 1, 2, and 4 are not in series. 1, 3, and 4 are not in series. Not even 1. 1 and 4 are in series. Yes. Yes. You can make them, you can add them and make them one resistor if you want. You can add 1 to 4 and make them as one resistor. Yes, they are in series. As long as they have the same current going through them, then yes, they are in series. But be careful if there are some other connections within that circuit that may not allow you to move, then, but yes, those are in series. Yes, you can do that. This one, what about? Zero resistance, yes. Zero resistance, he will not allow any current to go into the other branch. But if there are finite resistance, then there will be, you know, a ratio. The smaller resistance will have the greater current and so on and so forth. Because at the end, you're going to have the same potential difference. And if they have the same potential difference, so here, let me show you I have this resistor, R1 equals, let's say, 10 ohms. And I brought another resistor here. I connected it in parallel, but this one is 1 ohm. Let's assume that the potential difference across both, delta V here equals to 10 volts. It's the same, right? The same for both of them. Then if you calculate the current, let me call this one I1, and let me call this one I2. Then I1 is delta V divided by R1. I1 is delta V 10 divided by 1, which is 10 amperes. Now I2 is delta V divided by R2, which is delta V divided by 10 ohm, 1 ampere. So you can see the ratio between I1 and I2, but there's still current in I2, right? But if this resistance is 0, then all the current is going to go through that path, and no current is going to go into the other path. Yes. Any other questions? Yes. We solved a question like that in last week, I guess, where we, if you recall, we had a uniform electric field, and the electric field was given to me. Then we had a particle, a charged particle with an initial velocity entering this uniform electric field. Now, what's going to happen here, let's assume that this is an electron. If you recall the expression, F equals QE, and we said that's small letter q. If it's positive, then the direction of the force agrees with the electric field. If this is small letter q is negative, then the direction of the force in the opposite direction of the electric field. So right now we have it as an electron, which means the small letter q is negative. And in this case, the electric force would be pointing this way. Now, this electron has a mass. Right? And in this case, Fe equals to ma. And Fe is QE. So from equating those two expressions, you can calculate the acceleration. For example, if you know the length of this plate, which is delta x, and you know the initial velocity, which is along the x, and that's going to stay constant because there's no acceleration along the x, right? So you can still use the kinematics to calculate, for example, the time. If you know the initial velocity, if you know the delta x, you can get the time from the time. This time you can use also to calculate the deflection. We did an example like this. where if you recall, we calculated the delta y, the drift along the y-axis. All those were calculating using the kinematics. So once you find the acceleration, you have velocities. You don't need to know anything about the forces after that. You have the acceleration, you have the velocities, you have the displacement. You can use the kinematics equations. No, you don't. You don't. Those numbers are usually provided to you in the formula sheet. I want you to look at the formula sheet. If you haven't done so, look at the formula sheet and see if you find anything that you would like to suggest adding to it. If it makes sense, I will add it. If it doesn't make sense, I will not add it. Usually, you will see some expressions can be easily derived. Of course, if you know how to deal with those equations, you'll find that those expressions or those equations that you need are easily derived from another equation. Like, for example, this power, right? Probably, I may not include all of them, but once you know Ohm's law is there, the power equals to delta VI is there. You can usually manipulate them. So sometimes for space space purposes, we don't include all the equations. Equations that can be easily derived are not included. But yeah, that's the way it goes. But make sure that we will provide you with all needed equations that you need to solve those, those problems. Any other questions? Questions? Probably not going to have time to solve the examples that I prepared for you, but you may see them posted on the, under the lecture later on. Probably I will combine some of them, add them to this, and post one recorded lecture that has all of them. So, any question before we end the session? No questions? Okay. So, let me see if I can go through one example here. We still have 8 minutes. Okay, so we have an electron that is released from rest at an unknown distance above a positively charged plate. The plate produces an electric field of magnitude 4.2, 10 to the power 3 newtons per coulomb upward. The electron hits the plate with a speed of 6.9, 10 to the power 6 meters per second. Use energy methods to determine the distance from the plate that the electron was released. Okay, so how do we solve for this problem? What do we have here? We have a positively charged plate. We have an electron here that we have released. So positively charged plate, electron here, particle here, then we will be using the location of this particle as our reference for the displacement using this expression. So in this case, this level is my 0, y equals to 0. And pointing toward the positive plate is the positive displacement. So what's going to happen here, this electron, once I release it, it will accelerate in this uniform electric field, come hit this positive charged plate. Now keep in mind that I have released it from rest, which means now Vi is 0, right? So what do I have here? I have the mass of the electron given to me 9.11 10 to the power minus 31 kilograms. I have the magnitude of the electric field, which is 4.2 10 to the power 3 newtons per coulomb. And also the final speed of the electron, 6.9 10 to the power 6 meters per second, was given to me. Where is that VF? This is the VF. At this point, this is the final, and this is the initial. So this is VI. VF is also given to me. What do I need to find? I need to find the height. Now keep in mind that my location of the particle, which is the electron, is my reference and my positive pointing downward. So if I am to measure this height, then this y is going to be from here down. I'm starting from here, going this way down, then I'm going positive y. So in this case, if I apply the conservation of energy, I have delta U equals to minus delta EK, or UF minus UI equals to minus EKF minus EKI. Now, keep in mind, since VI is 0, I have EKI equals 0 since VI is 0. I have UI equals 0 since Y is 0 at that location. So in this case, I have this one 0 and this one also 0. And this gives me UF equals to minus EKF. So what is UF? Let's go back to UF. Q electron, which is minus 1.602 10 to the power minus 19. E positive because it's a magnitude. Y also positive because I'm pointing in the positive direction. So what do I get here? I get UF equals 2 minus 1.602 10 to the power minus 19 times 4.2 10 to the power 3 times Y, and this is joules. Or UF equals to minus 6.73 10 to the power minus 16 Y joules, right? Is that right? This is UF. What about EKF? EKF is half m BF squared. EKF is half times 9.11 10 to the power minus 31 and 6.9 10 to the power 6 squared. EKF is 0.96 times 9.11 2.17 10 to the power minus 17. Now, if this is 1, this is 2, yeah, this is joule, this is 3. Now, if I substitute 2 and 3 and 1, what do I get? I get minus 6.73 10 to the power minus 16. Y equals to minus 2.17 10 to the power minus 17. And then if you do the calculation, you will find that y equals to 3.22 10 to the power minus 2 meters, or 3.22 centimeters. Okay, so let me stop here.